Hello everybody, let us solve determinant exercise 4.2 from NCERT. So the first question is given as using the property of the determinant and without expanding we have to prove this determinant to be 0. So what to be done? Let's write first. The determinant is x a, x plus a, y b, y plus b, z c, z plus c. So by writing only, whenever you'll write any sum, so you can guess if you have the proper preparation. So let us see. In this case, column 3 x plus a, column 2 first element a, column 1 first element x. So let's make one new column 3 which goes to C3 minus C1 minus C2, and our target is to make maximum number of zeros because here it has been given without expanding the determinant using the property only. So we are operating on C3, therefore C1 and C2 are remaining same. So A, B, C. Now on C3 x plus a minus x, this is 0. Similarly y plus b minus y, that is also 0, and z plus c minus z. So we know that if any one row or column is 0, then the full determinant is coming to be 0. So the answer is 0, and which is proved. We had to prove the answer to be 0 and we have proved this. So everybody, let's go to the next sum. The question number 2 is given. Using the property and without expansion, similar type, similar meaning, prove that the determinant, I am writing the determinant, this is a minus b, this is b minus c, this is c minus a, b minus c, c minus a minus b, c minus a minus b, b minus c. So in this case we can do operation on suppose C1 or C2 or C3, suppose on C1 because the thing is symmetrical. On C1 if we make the operation, that is C1 plus C2 plus C3. So if we make the operation on C1, we are getting here a minus b plus b minus c plus c minus a, that is 0. Similarly b minus c plus c minus a plus a minus b, this is coming 0. And this is c minus a minus b, b minus c, similar with a 0. And other rows and columns are unchanged. A minus b, that is a minus b, b minus c. So answer is coming 0. So we have to apply in proper way the properties. So let's go to the next sum. In this sum number 3, similar expression. The expression is totally similar using the properties of the determinant and without expanding. So let us write this. 2, 7, 65. We have to try to get some similarity. Always 75, 86. What to do? This column containing the bigger elements. So what can be done here? 7 9s are 63, it is nearer to the 65. 8 9s are 72. So let us apply one thing. So on C3, let us make one operation, that is C3 minus 9 C2. If we make this operation, we are getting here 2, 3, 5, 7, 8, 9, 65 minus 63, that is 65 minus 63, and in this case 75 minus 72, 8 9 is 72, so 75 minus 72 and 86 minus 9 9s are 81. So 86 minus 81. So this is coming to be, we are getting 2, 3, 5. Here it is 7, 8, 9, and this is 2, 3, 5. And we are seeing that these two rows, these two columns are identical. Therefore, the determinant is coming 0, because there is a property that if any two rows or columns are identical, then the value of the determinant is coming to be 0. Let's go to the next sum. Same statement, using property, we have to prove that this determinant to be 0. So let's start. The determinant is 1 1 1 BC CA AB. Here A into B plus C, B into C plus A, C into A plus B. We have to make it 0. So column 3 is the big column. So let us see one thing, AB, AC, and it is BC. BC, AB, this is CA. So on this column 3, if we make this operation, that is C3 plus C2. Let's see what is coming. In this case, we are seeing here, other columns are unchanged. So BC, CA, AB. So on column 3, C3 plus C2. So AB plus BC plus CA. Here also, in this element also, AB plus BC plus CA. Here also, AB plus BC plus CA. So there is a common factor, we can take it common. So we can take AB plus BC plus CA common. So we are getting here AB plus BC plus CA. If we take common, we are getting 1 1 1. This is BC CA AB 1 1 1. Similar to that the last sum. So if any two rows or columns are identical, determinant is coming to be 0. So in this case, column 1, C1 and C3 are identical. Therefore, the value of the determinant is coming to be 0. Now, let us go to the next sum. For this question number 5, the condition is a similar condition. So, without expansion. So, let us write this determinant once again. So, in this case, B plus C, Q plus R, Y plus Z, C plus A, R plus P, Z plus X, A plus B, P plus Q, X plus Y. So we have to get to this format. It means there are double elements here, and here we have to get in single format. What to be done? First of all, what can be done? Let us interchange rows and columns. So if we interchange the rows and columns, we are saying that B plus C, C plus A plus B, Q plus R, R plus P, P plus Q, and here Y plus Z, Z plus X, X plus Y. Now, we have to make at least one column with the elements single. So, what can be done? Let's on C3, let us make one operation which is C3 minus C1 minus C2. So, if we do this operation, what is coming here? So, on C3 we are changing on C3. So, C1 and C2, column 1 and column 2 remaining the same. Therefore, here we can write this as B plus C, Q plus R, Y plus Z, C plus A, R plus P, Z plus X. Just say one thing. On C3, the operation is C3 minus C1 minus C2. So, what is coming here? A and B is getting cancelled. We are getting minus 2c minus 2r minus 2z. From this, by the k property, we can take minus 2 common. So, if we take minus 2 common here, we are getting b plus c, c plus a, other two column I am writing first, q plus r, y plus z, r plus p, z plus x, and here it is coming c r z. Just notice one thing, this is c r z, this is c r z. Notice this, everybody. Therefore, now the operation becomes easier, because first of all we have to get into one element. After that we can interchange. Let's see. So we'll apply now one operation on C1, that is C1 minus C2, and another operation C1 minus C3 it is, and another operation, because our target is to make the elements one element in each rows and columns, and on C2, that is C2 minus C3. If we do this, we are seeing that minus 2 is here, then b plus c minus c, that is b, similarly q plus r minus r, that is q, similarly y, similarly for the C2, that is c and c is getting cancelled. So, apx, and it was c r z, but we have to get this form. First of all, let us interchange apx, this is apx, this is apx, in this column it is apx, okay. So, first of all, let us interchange C1 and C2, and for each interchange we know that it has to be multiplied by minus 1. Therefore, if we make it C1 and C2, if we interchange, then this is coming to be minus is absorbed, this is coming 2 into apx bqy and crz. But we are seeing that apx, bqy, crz, they are in the row wise. So, let us interchange rows and columns, determinant is, it has been proved. So, if we interchange rows and columns, we are getting here apx, bqy, c, it was c, this is r, this is coming to be r, c and c r z, and this is our requirement, and the question is proved. So, let us go to the next sum. Next sum, sum number 6. Here we have to apply that, we have to make it 0. Answer is coming 0. It is better if we can show any two rows or any two columns are identical. So, what to be done? Let us see this. First of all, I am writing 0 a minus b minus a 0 minus c b c 0. So, let us select the row number 1. So, on the row number 1, if we multiply by c, so balance by 1 by c, I am multiplying row number 1 by c. So, balance by 1 by c. So, this is coming 0. So, this is coming AC minus BC. Then other rows are remaining the same, minus A 0 minus C B C 0. I have multiplied by C, so balance by 1 by C. Now what to do? If we make this operation on R1, so R1 minus B R2. So what to do here? This is coming AB. Here it is coming AC. Here it is coming 0. And other are remaining the same, minus A, 0, minus C, B, C, 0. Here it was 1 by C. Now I am taking A common from the row number 1, because always you have to keep in mind, whenever answer is coming 0, always you have to keep in mind that any two rows or columns should be identical. Okay. Generally, in the general case, there are exceptional case also. Now if we take A common, so A by C, we are getting BC 0 minus A 0 minus C, that is BC 0. So we are seeing here that row number 1 and row number 3 are identical, therefore the determinant is coming 0. In this sum, so everybody, we are solving the NCERT books and exercise number 4.2. So in this sum, we have to take some common. So from the R1, from the row 1, if we take A common, from the row 2, if we take B common, and from the row 2, if we take C common, let's see what is coming. So A common from the row number 1. So I am taking A here, I am taking first, I am writing this thing, minus A, B, C, and B common from the row number 2. So we are getting here A minus B, C, and C common from the row number 3, and we are getting here A, B minus C, and outside it is A, B, C. Now once more, we can take A common from the column number 1, B common from the column number 2, C common from the column number 3. So we are getting another ABC, that is A square, B square, C square, and it is coming minus 1, 1, 1, 1, minus 1, 1, 1, 1, minus 1. Okay. Now there are number of 1 and minus 1. So we can do like this. We can apply on R1, suppose R1 plus R2. If we apply this, we are getting A square, B square, C square, and on R1, R1 plus R2, this is 0. Similarly, second element is also 0, and third element is coming 2. So 1 minus 1, 1, 1, 1, minus 1. Now just see if we can A square, B square, C square, and if we just start expanding, we are getting 0, 0, and 2 into, if we just remove the row and column related to 2, what we are getting? 1 plus 1, that is coming 2. Therefore, your left cross minus your right cross, it means this is coming to be 2. Therefore, 2 into 2. Therefore, 4 A square B square. Sum is proved. The answer was 4 A square B square C square. It is C square will be there also. 4 A square B square C square is the answer. Now, let us do the next sum. Sum number 8, part 1. So in this sum, 1, 1, 1, A, B, C, A square, B square, C square. I think this is easier for you. So what to do? There are number of ones. So let us apply. We have to make the number of zeros. That target will be always to make the number of zeros so that calculation becomes easier for us. So on R1, let's make operation R1 minus R2. On R2, let's make operation R2 minus R3. So we can write this as on R1, let's make an operation R1 minus R2, and on R2, this is R2 minus R3. Now if we calculate, we are getting 1 minus 1, 0, A minus B, A square minus B square. Similarly, on the R2, 1 minus 1, 0, this is b minus c and b square minus c square, and third row remaining the same. From the row number 1, if we take a minus b common, from the row number 2, if we take b minus c common, what is coming? Here it is coming a minus b into b minus c. We are getting 0, 1 a plus b, 0, 1 b plus c, and 1 c, c square. If further we could do like this. Again R1, on R1 we could operate on R1 equals R1 minus R2, but it is unnecessary. There are two number of zeros, we can directly multiply. Therefore, let us expand. So a minus b into b minus c, and on expansion, if we expand column wise, 0 into anything, this is 1. If we take 1, so neglect the row and column related to 1, your left cross minus your right cross, that is b plus c minus of a plus b, that is what is coming here, that is c minus a. Therefore, final answer is a minus b into b minus c into c minus a, and which is the proof. Let us do the next sum. One such similar sum. Once again, similar operation. Let us operate. Since there are number of 1, 1, 1, so here in column, so operation should be C1 on C1, C1 minus C2 on new C2 will make C2 minus C3, or so on C3, C3 minus C2, as you think better, any two subtractions, so that we will get the number of zeros. Therefore, first of all, the operations should be on C1, C1 minus C2, and on C2 another operation, that is C2 minus C3. If we operate, we are getting here 1 minus 1 0, a minus b, a cube minus b cube, and on C2, that is 0, b minus c, b cube minus c cube, and 1 c, c cube. From the first column we can take a minus b common, from the second column we can take b minus c common. What is coming here? 0, 0, 1, 1 a square plus ab plus b square, and here 1 b square plus bc plus c square, and here it is, just I am changing this. This is 1 c, c cube. So there are number of zeros. We can directly multiply. Otherwise, we can do once again on C1, that is C1 minus C2. That is also possible. Otherwise, we can multiply as you think better. So let us multiply. A minus b into b minus c. Now if we are going to multiply, that is your left cross. If we neglect row and column related to 1, your left cross minus your right cross. So b square plus bc plus c square, b square plus bc plus c square minus a square minus ab minus b square. Now let us calculate. A minus b, b minus c. If we calculate here, what we are getting? This is b square is getting cancelled, and from these two, BC and AB, what is coming common? If we take B common, this is C minus A, and here it is C square minus A square. I am writing C minus A into C plus A. If we calculate further, so we are getting once again B minus C into, okay, I am writing from the beginning better, A minus B into B minus C. Now C minus A is coming common, and we are getting A plus B plus C, and sum is proved. So this is C minus A into A plus B plus C. So everybody you have to solve the sum. This sum is not very hard. This is easy because 1, 1, 1 is there, but for the entrance examination hall, the solving the determinant is really the headache. You have to practice too much. So let's solve sum number 10 part 1. In this case, we are seeing that x plus 4, 2x, 2x, 2 plus 2, 4 plus 1, 5. In this case, 2 plus 2, 4 plus 1, 5. 2 plus 2, 4 plus 1, 5. It means if we just add the columns, the value is remaining the same. Therefore, we can apply here on C1, let us operate C1 plus C2 plus C3. So, we are getting here 2x plus 2x, 4x plus x, that is 5x. 5x plus 4, 2x, 2x, 2x. Similarly here 5x plus 4, x plus 4, 2x, and here it is 5x plus 4, 2x, x plus 4. So we got the formation. Now we are taking this common, we are getting 1, 1, 1, and our every attempt will be to make 0, 0, 0. So in this case we can take 5x plus 4 common, we are getting 1, 1, 1. So 2x, 2x, this is x plus 4, 2x, and here 2x, x plus 4. Now if we apply that R1, on R1 let us apply one operation R1 minus R2, and on R2 let us apply one operation R2 minus R3. So we are getting the number of zeros. So here we are putting here 5x plus 4 common, and this is 1 minus 1, 0, 2x, 1 minus 1, 0, 2x minus x minus 4, it means x minus 4, x minus 4. So 2x minus 2x, 0, there are number of zeros we got, and once again R2 minus R3, 1 minus 1, 0, and here it is coming 4 minus x, and this is x minus 4, and here it is 1, 2x, x plus 4. Now we can take r minus 4 common, we can take x minus 4 common from the row number 1, we can take x minus 4 common from the row number 2. So there are two number of x minus 4, so 5x plus 4 into x minus 4 whole square. So we are writing this as 0, 1, 0, 0 minus 1, 1, 1, 2x, x plus 4. Further calculation needed? Unnecessary, because there are two number of zeros. We can expand through row or column. Therefore, if we take the common, that is 5x plus 4 into x minus 4 whole square, and if we expand through the column, so we are getting here your left cross minus right cross. So this is 1. Therefore 5x plus 4 into x minus 4 whole square, and this is the answer. So x minus 4 whole square and 4 minus x whole square is same. Therefore, let us go to the next sum. Here also similar sum, y plus k, y, 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 y plus k, y, 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 y plus k. That is, if we add the column wise on C1, suppose C1 plus C2 plus C3, so we can take common. So it is better if we can take on C1, we can apply C1 plus C2 plus C3. So y plus y plus y, 3y, 3y, 3y plus k, y, y, and this is 3y, same thing, 3y plus k, y plus k, y, this is 3y plus k, this is y, y plus k. Now we can take this thing common. Therefore, I can write here equal to, if we write 3y plus k common, we are getting 1 1 1 y plus k y plus k. Now we have lot of option. We have lot of option in hand. Better on R1 make operation R1 minus R2 and on R2 minus R3, because our target is to get number of zeros. So on R1 make R1 minus R2 and on R2 make one operation R2 minus R3. Let's see what is coming. Here it is coming 3y plus k. What do you have to prove? Multiplied with the k square. So on R1 minus R2, this is 0, y minus k, that is minus k, 0. On R2, 1 minus 1, 0, this is k, this is minus k. So this is 1 y plus k. So from the row number 1 we can take common k minus k, as you think better. We can take k common. From the row number 2 also we can take k common. Therefore we can write 3y plus k. There are 2k, that is k square, 2 number of k. From row number 1, 1k. From row number 2, another k. So we are getting 0 minus 1, 0, 0, 1 minus 1, 1 y plus k. Now if we expand through the row number, suppose column number 1 or row number, as you think better. If we expand through the column number 1, so just minus 1 into minus 1, that is 1 minus 0. So final answer is coming to be 3y plus k into k square, which is the proof. Now let us go to the next question. Sum number 11. Here we have to prove this determinant equal to a plus b plus c whole square. So always you have to try to search some symmetry so that we can operate from there. For example, a minus b minus c, 2b 2c. If we operate like this, R1 equals R1 plus R2 plus R3, we will get some common. Let's see. On R1, let us operate R1 plus R2 plus R3. If we operate on R1, we are getting here a plus b plus c, a plus b plus c, a plus b plus c, and other rows are unchanged, 2b, b minus c minus a, 2b, 2c, 2c, c minus a minus b. From the row 1, if we take a plus b plus c common, so if we take a plus b plus c common, so we are getting 1 1 1, 1 1 1, 2b, 2c, b minus c minus a, 2c, 2b, c minus a minus b. Now on R1, on C1 let us make C1 minus C2, and on C2 let us make C2 minus C3. Same process as usual because there are number of ones. So a plus b plus c. So we can apply on C1, C1 minus C2, and on C2, C2 minus C3. Therefore, in this case 1 minus 1 0, 2b minus b minus c minus a, it means a plus b plus c. Actually our target is that whatever there here, whatever there will be here, we have to take as much as possible the factors common. So in this case on C1, C1 minus C2, 1 minus 1 0, here 2b minus b, that is b, plus c plus a, that is a plus b plus c. This is 0. On C2, once again, on C2, C2 minus C3, 1 minus 1 0, b minus c minus a minus b, that is minus of a plus b plus c. Therefore, minus of a plus b plus c, and here 2c minus c minus of minus a minus of minus b, it means a plus b plus c, and finally 1 2b c minus a minus b. From column number 1 we can take a plus b plus c common, from column number 2 we can take a plus b plus c common, so much common, and we got our requirement a plus b plus c whole cube. Therefore, we can proceed like this. A plus b plus c, from the column 1 we can take a plus b plus c 1, from column 2 we can take a plus b plus c, so a plus b plus c whole cube, and the determinant is coming 0 1 0 0 minus 1 1 1 2 b c minus a minus b. If we expand through row or column, the matter is same. Therefore, it is coming to be a plus b plus c whole cube. Now 0 into anything that is 0. So, your left cross minus right cross, therefore answer is coming into 1 minus 0, that is a plus b plus c whole cube. Over. Let us go to the next sum. It means we have to see one thing here, that whatever may be given to prove the factors, you have to get a maximum number of factors outside before expansion. Otherwise, in the examination hall, determinant is really a problem. Next. This is another such sum, like previous sum. For this sum, let us apply the similar process. So, x plus y 2z x y. So, let us apply C1 on C1, C1 plus C2 plus C3, and we are getting the common, that R1 equals R1 minus R2, R2 equals R2 minus R3. In this way, we will proceed. Okay? So, let us proceed. I am applying the condition on C1, C1 plus C2 plus C3. So, if we apply, we are getting, what is coming here? X plus y plus 2x, 2 into x plus y plus z, and in this case 2 into x plus y plus z, in this case 2 into x plus y plus z. X, y, y plus z plus, here it should be 2x, it is a printing mistake here, y plus z plus, this is coming 2x, x, and here it is coming y, y, z plus x plus 2y. From the column number 1, if we take the 2 into x plus y plus z common, so we are getting 2 into x plus y plus z common, we are getting here 1 1 1 x y, y plus z plus 2x, this is y, and here it is coming x, same as this previous sum, z plus x plus 2y. Now, same as the previous method, suppose R1 equals, on R1, we are doing continuously on R1, let us apply on the R2. R2, on R2, R2 minus R1, on R3, R3 minus R1. Let's see what is coming. So, the operation will be on R2, R2 minus R1, on R3, R3 minus R1, because let us see now, number of times we have not just keep R1 as it is. So, let us keep R1 as it is. Now, it is coming R1 is as it is, because continuously we are changing the R1. Let us see, if we do not change the R1, what will be the problem? So in this case R2, on R2, R2 minus R1, that is 0, and y plus z plus 2x minus x, that is x plus y plus z, and 0. Similarly on R3, R3 minus R1, on R3 it is coming 1 minus 1 0. There are so much zeros, and x plus y plus z. And it was 2 into x plus y plus z. 2 into x plus y plus z it was. Now take number of terms common. So 2 into x plus y plus z is there. From the row number 2 we can take x plus y plus z common. From the row number 3, same as this previous sum, x plus y plus z common. So x plus y plus z whole cube, and we are getting 1 x y 0 1 0 0 0 1. Now if we expand through, instead of expanding through the row 1, what I told you, it is unnecessary, better expand through the C1 column 1. So if we expand through the column 1, we are getting 2 into x plus y plus z whole cube, and if we changing, that is 1 minus 0, final answer is 2 into x plus y plus z whole cube. So this is the answer of the question. Now next up, by using the properties of the determinant, show that 1x x square 1 x square 1, same as this previous. So better on R, on C better, on column C1, on C1, C1 plus C2 plus C3. So let us operate on C1, C1 plus C2 plus C3. So if we operate on C1, that is 1 plus x square, 1 plus x square, 1 plus x square, that is x square 1 x square 1. If we take common here, if we take 1 plus x square common, we are getting 1 plus x square common, getting 1 1 1. Same as this case. Now we have to do R1 on R1 minus R2, on R2 minus R3, same as this. So we are getting x square 1 x square 1. Now 1 plus x square, let us operate in this way on R1 minus R2 and on R2 minus R3. Let us operate. We are getting what? First of all, 1 plus x square. So 1 minus 1 0, x minus 1, and x into x minus 1. Actually x square minus x, I am writing x into x minus 1. Next, R2, 1 minus 1 0, 1 minus x square, x minus 1, and for the 3, 1 x square 1. Now we have to take number of portion common. What to do? 1 plus x square common. We are taking from the column number 2, we are taking x minus 1. Therefore, no, from row number 1 we have to take x minus 1. From the row number 2 we can take x minus 1. So x minus 1 whole square. So this is coming 0 1 x. From the row number 2 we are taking x minus 1 common. So 0 minus of x plus 1, 1 and 1 x square 1. So already we got lot of common, and here also number of zeros are there. So I think it is unnecessary to further simplification. Therefore, we can multiply through the column number 1. So final answer is 1 plus x square into x minus 1 whole square, 1 minus of minus plus. So this is coming 1 plus x into x plus 1, just small portion which we have to expand. Everybody remember one thing, for the entrance examination, this is really a problem, this determinant. So we have to get out of all the factors, maximum factors, okay. Then what is coming here? 1 plus x square. So it is 1 plus x square whole square, x minus 1 whole square. So we are getting here a minus b into a square plus ab plus b square, that is x cube minus 1 whole square. Sum is over. For question number 13, so the question is 1 plus a square minus b square, 2ab minus 2b, 2ab 1 minus a square plus b square. So this is 2a, 2b minus 2a, 1 minus a square minus b square. So totally not symmetrical. So what to do? How to solve this type of sums? So that is why instead of solving the sum, I am explaining you. So how to just solve this type of sums? Say this. In this case, one minus a square minus b square. So on R1, let us operate R1 plus, we could operate same thing in column 1 also. So on R1, let us operate on R1 plus b R3. So if we multiply b here, so actually 2b square. So if we add on R1, so 1 plus a square plus b square, because our need is this 1 plus a square plus b square, that is why. So 1 plus a square plus b square. In this case, if we multiply this by b, so 2ab minus 2ab, in this case minus 2ab plus 2ab is 0, and in this case if we multiply this by the b and then add, so minus b it's coming, it I am showing you. So for this element I am showing you for this element. So in this case minus 2b, and I am multiplying this by b and adding, plus b into 1 minus a square minus b square. Actually the calculation is this. It means this minus b into, because if we take minus 2 plus 1 minus and all minus is coming common, okay, I am showing you, that is minus b if we take common 1 plus a square plus b square. Actually it is coming here. Similarly on R2, this is R2 minus a R3, it will be there. It has been some printing mistake. Oh. Same calculation. It's the same calculation. So R2 minus a R3. So if we multiply by a and subtract, it is coming 0. If we multiply by a, so minus a square minus of minus a square plus. So this is coming. So same operation here. And we are taking here from the first row, we are taking 1 minus 1 plus a square plus b square, and from the second row also 1 plus a square plus b square. So we need the 3 1 plus a square plus b square. We need 3 1 plus a square plus b square, but here we got already 1 plus a square plus b square, 2 number of. It means once again we are taking 1 plus a square plus b square from the first row, 1 plus a square plus b square from the second row. Then 1 plus a square plus b square whole square, and the values are coming like this. One 0 minus b, 0 1 a, and third row is unchanged. This is the thing. Now let us expand. Further calculation is possible. Better let us expand. Whenever we cannot understand what to be done, no symmetry, let us expand. So we can do one thing. Let us expand through R1, or we can expand through C1 also. Okay, let us expand through R1. We are getting what? 1 into this portion, that is 1 into this part, this determinant. This is the thing, 1a minus 2a and this, and minus b into this determinant, this. Now if we just cross multiply, 1 into 1 minus a square minus b square, minus of minus, that is plus 2a square. Similarly minus b, this is 0, minus of minus 1 plus 2b, we are getting our result. Therefore the final answer is coming 1 plus a square plus b square whole cube. We need to practice this type of determinant, because when this type of determinant is coming, this is something confusing, that what to be multiplied and what to be added. But we need what is the requirement. This type of sums are coming in board examination. Whatever requirement, we have to practice continuously, mainly this type of sums. Once again, I am going to the next sum. Sum number 14. Here is also such type of sums, no symmetry. Then how to proceed this sum? First of all, if we take a, b, c from the a from the R1, if we take a from the R1, a common from the R1, so a is outside, and a square plus 1, if we take a common, that is a plus 1 by a. The thing is this. Similarly, we can take b common from R2, c common from R3. We are getting this. Now let us operate. R2 equals R2 minus R1, and R3 on R3, this is R3 minus R1. So if we operate like this, what is coming? Let's see once. A, B, C outside, because we have taken common. So R1 remaining unchanged, B, C, and on R2, R2 minus R1, this is minus 1 by A, and R2 minus R1, it means 1 by B, 0, and for R3, R3 minus R1, it means here also minus 1 by A, this is B minus B, 0, this is 1 by C. We got this. Same step is there. Now it was ABC previously. Now we can multiply first column by A, second column by B, third column by C. So we have multiplied A, B, C, and so we have to balance also. We have to take outside 1 by ABC. So there is outside 1 by ABC, and they are getting cancelled. Now if we multiply A with the first column, this is A square plus 1, similarly minus 1, minus 1. B with the second column, that is, this is coming B square, 1, 0. Similarly C with the third column, we are getting this. Now so further simplification possible. So we can do like this, that R2 equals R2 minus R1, but unnecessary. We can expand through, it is better R3. We can expand through R3. It's a printing mistake again here. So this is, if we expand through R3, minus 1 into, if we take minus 1 into, here it is coming, this determinant, and I am changing this, and 0 into anything, and plus 1 into this determinant. Now if we just cross multiply, B square into 0 minus C square, similarly if we multiply, we are getting this delta, it means determinant equal to 1 plus A square plus B square plus C square. So these type of categories are very important, that we have to multiply, you have to take common, you have to practice continuously. Let us do the next sum. Sum number 15. In this case, choose the correct answer. Let A be the square matrix of order 3 into 3. So everybody, matrix to determinant and determinant to matrix is very frequent, very common for entrance examination like joint entrance examination, IIT, JME like that, WBJ. So if for board examination also it is extremely important. So let's see this. First of all, let us consider one matrix, that is A. So this is coming A1, B1, C1, A2, B2, C2, A3, B3, C3. Suppose this is a matrix. Now let us multiply K with the matrix. Therefore, Ka, and we know that there is a property of the matrix, K property, which is commonly called, that is, if any constant K is multiplied with the matrix, then every element will be multiplied by that constant. Therefore, we can write this as Ka1, Kb1, Kc1, Ka2, Kb2, Kc2, Ka3, Kb3, Kc3. Now, according to this question, we are converting this matrix to the determinant. It means determinant of Ka equal to this becomes now determinant, and as we know that the value of the matrix is called the determinant, and obviously it should be the square matrix. Now Ka1, Kb1, Kc1, Ka2, Kb2, Kc2, Ka3, Kb3, Kc3, Kc3. But there is a difference in K property of the matrix and determinant. For determinant, the K property is that if in any one row or column, if there is a constant, we can take it outside. But for the matrix K property, every element, if there is a common, then we can take K common. So from this, we can take K common from the first column, we can take K common from the second column, we can take K common from the third column. Therefore, we can write this as K cube into A1, B1, C1, A2, B2, C2, A3, B3, C3. It means this is coming K cube into mod A. So which option number is getting satisfied? The option number is the C. This is a C, option number C is getting satisfied. Next. And this is the last question of this chapter. Which of the following is correct? Option A, determinant is a square matrix. So everybody, determinant is not the matrix. So matrix is a system and determinant is a value. So option A is wrong. So option A is not right. Option B, determinant is a number associated to a matrix. Yes, determinant is a number associated to a matrix, but the matrix should be square matrix. What I told you the last time. Therefore, this is wrong. And option C, determinant is a number associated to a square matrix. So option C is the right. So everybody, that's all. So I'll get this type of videos regularly. So subscribe the channel.